Okay, it is November the 12th, 2020. I wanted to work out one or maybe two examples for calculating beam deflection. The first method is the moment area, and just need you to remember that it's primarily, or what I want you to know to use it for, is cantilevered beams. So I think it was problem 40 of your last homework. You had something like this. We had a 30 kip load that was 10 foot from the fixed end, and then you had a 20 kip load that was located at the free end or 20 foot away. So, you know, when you do the reactions for this, you get 50 up, and the moment reaction is 30 times 10 is 300, and 20 times 20 is 400, so that gives us 700. So how the moment area method works is we actually do a moment diagram. So we would drop down here to 700, and what we actually do is put everything over EI. So it's an M over EI diagram, but it's nothing more than your moment diagram. Now let's call this, I think this was point B. I'm going to call it point B, and that point A. It could be backwards, but that's okay. So what is the moment at point B? Well, you know, we can cut a section right down through here and look to the right. And all you'll see when you do that is you'll see the, 20 kip load. That's 10 foot away. And that's to the right of our section. Call that section 1-1 if you want. So the moment there is 200. So there's something like this. And then, of course, all the way at the end, if we cut a section at the end, we would see nothing when we look to the right. So, obviously it goes back to 0 there. So this is actually 700 over EI, and then it goes to 200 over EI, like that. So that's your M over EI diagram. So what we need to do is break that up into shapes. Now you could do this with two triangles if you want, or we would really, since we're interested in slope at B and slope at A, and then deflection at B and deflection at A, we want to kind of divide everything at those points, or have a division, you might say, at that point. So I'm going to do shapes like this, and I'll just call this shape 1, and this shape 2, and then shape 3. So I have shape, and then I have the areas of those shapes that are calculated. So remember, this point right here is 200. So shape 1 is just 200 times 10, or 2,000. Shape 2 is half of 700 minus the 200, so that's 500. Half of that's 250 times 10, so that would be 2,500. And then shape 3 is half of 200, which is 100, times 10, which would be 1,000. All right, so those are our areas. So slope, if you'll look back to your chapter notes that I posted separately, slope is simply the area, or areas you might say, of the M over EI diagram out to the point of interest. So slope is simply going to be, we have shape 1 and shape 2 that are out to, if we're finding the slope at point B. So that would be 2,000 plus the 2,500. Shapes 1 and 2. And then that's over EI. I think for this problem, we'll say 29,000 kip per square inch. That's typical for steel. And then I think it might have been 2,500 inches to the fourth. Now, if your diagram is in kips and feet, everything, and then your modulus elasticity is in kips per square inch, and your I's in inches to the fourth, we have to multiply this to make the units work by 12 squared. So we actually have 4,500 divided by 29,000 and divided by 2,500 times 144, which is 12 squared, and we get a value of 0.00894, and it could probably go on radians. All right, now let's look at out to A. So out to A, we got the 2,000, we got the 2,500, and then we've also got shape 3, which is 1,000, and that's all over EI and all times 12 squared. So when you do that, let's see, that's 5,500 divided by 29,000 divided by 2,500 and times 144. For that answer, I'd get 0.01092, and that's also in radians. So that's how we find the slope. Yeah, you know, and what slope is basically measured from that horizontal. It's the angle. So at this point would be at B. What's that angle right there? And for that angle, you know, delta A of the deflection. Now we can take that same information, and deflection at point B is defined as the moment of the area about the point of interest. So what do I mean? Well, each of these areas has a centroid. And if our point of interest is, you know, here, point B is right along this line, then the centroid of a rectangle is halfway in the x direction. So, you know, in the x direction this way, it's halfway or 5 feet away. So that first area, 2,000, referencing to this number here, times 5. Plus the 2,500 times its centroid is 1/3 of the way, or actually be 2/3 from point B. So 2/3 of 10 is like 20 by 3. That's like 6 point repeating 6. I'm going to write 20 by 3, and your calculator, that's probably the best way to do that. 2/3 of 10. And that's it. That's all of the areas that we have to include out to point B, and that's over EI. And we have to make the units work out this time. We have to multiply by 12 cubed, or 1728. So let's try that one real quick. So 2,000 times 5, 2,500 times 20 by 3. Add that together. Divide by 29,000 and divide by 2,500. And then multiply by 12 cubed, or 1728. And in that case, I got 0.6356 inches, and that would be down the deflection. You can't have a positive deflection if you think about like a diving board, an overhanging beam, and you have the load between the supports, so the end could actually be going up. That'd be a negative. I don't remember that number. I'm going to check that again one more time. Check those numbers. 2,000 times 5, 2,500 times, I'm just going to use 6.7 as a check. Add that together, divide by 29,000, and divide by 2,500, multiply by 1728. I got the same answer, 0.63. Perhaps this number 40, perhaps these numbers right here were slightly different, but that's how you do that. Now let's try using these numbers, deflection at A. So we're kind of using this equation for the areas, but then we're putting in, you know, what is the multiplier there for the moment arm, okay? So 2,000 times, now this time it would be about point A, so we're going all the way out to the end. So instead of being 5, it would actually be 5 to get us to B, and then another 10, so it'd be 15, plus 2,500 times, well, it was basically 6.7, or repeating 6 here, so this is going to be 16 point repeating 6, plus, remember we got this last area here, that's 1,000, times its centroid is here, which is 2/3, once again, of 10. So that's going to be 6.6 repeating, all over top of EI times 12 cubed. So for this one, we get 2,000 times 15, 2,500 times 16, I'm rounding, 16.7, and 1,000 times 6.7. Add that together, divide by 29,000, divide by 2,500, and multiply by 1728 to get our units consistent, and so that we can report in inches. 1.86982 inches, and it is down. And that's how we do the moment deflection. The moment area method for beam deflection. So it's not too bad. I'm going to go ahead and just pause the recording, and I'm going to get set up, and we'll talk about moment of elastic weights in just a second. Method of elastic weights. All right, so this problem, I believe, is problem 50 of chapter 8. And this is where we would use the method of elastic weights. And also, you might notice on trusses, that's also the there's a method of elastic weights that you should be working on in chapter 9, I believe. But this for beams, we will use for a simply supported beam with the supports at the ends. So the first thing that I want to recognize about this problem and several others, I could go back to even the cantilevered beam, is we can always separate these. So if we have a beam that has a couple different kind of loads on it, so a uniformly distributed load and then also a concentrated load, so this is W and that's P, well, we can make that into two different problems. We can solve this one and then just add in this one to get our answer. So solve for deflection here, solve for deflection here. As long as we're solving for deflection at the same point of interest, say at the free end, then we can just add those deflection values to that. All right. So in this particular case, which is a very common beam loading case, we would have, this would actually be equal to, and the easiest way to work this problem is to break this thing up into this plus, we got distributed load plus concentrated load. So there's the, this I can go ahead and put in, this is the 20 kip, and this is the 1 kip per foot. Now, there are equations set up for common beam loading configurations and conditions. This one is actually pretty easy. The deflection for uniformly distributed load when you're calculating at the center line, so deflection at center line, which is what this problem asks for, it's actually 5WL to the 4th over 384 EI, and you may have found that. And then for a beam that's simply supported with a concentrated load in the center, it's PL cubed over 48 EI. Now, believe it or not, I didn't look at any references or textbook or notes or anything to know those. Why? Because those are common. And so I remember those. Now, keep in mind, both of these, or you can do it at the end, have to be multiplied by 12 cubed, just like before when we deal with kip as our units of load and feet as our unit of length. And then, of course, E needs to be in kip per square inch, and I, the moment of inertia, needs to be in inches to the 4th. All those are common, so don't forget to multiply by the 12 cubed. All right, now let me show you the method of elastic weights. At least I can show you kind of the concept here. And I am going to break it up just because it's easier to do that way, although I wouldn't have to. All right, so I'm going to do, as I mentioned, I'll just do it right here. This, we could say that the resultant load here, since this is 20 feet, remember, is going to be 20. So keep in mind the reactions just for this part are going to be 10 and 10. And the moment diagram is going to be a lot to a little, I'm sorry. A lot to a little, and this is actually, WL squared by 8. Another very common, so that's why I know that one. So if we go WL squared by 8, that's 1 times 20 squared, that's 400 divided by 8. We would get 50. That's 50 kip feet right there. All right, and then this one, this is also going to be 10 and 10 for the reactions. This one's going to be a straight line up to. If we cut that beam right here and we look to the left, all I see is this 10 times 10 feet, so that's going to be 100. All right, so that's 100 kip feet, and this is 50 kip feet. Now, the way that the method of elastic weights works is we actually put that back onto the beam, meaning that we have the same supports as we have in the original problem, and we load it with this. So now we've got kind of this weird load. We're going to divide it right in the center because we're interested in, that's the point of interest. Same thing for here, which is the same point. Remember, I just separated these two. We're going to end up adding them together. And we're going to find the reactions of the beam with the moment diagrams loaded on it. So you may have to look this one up as far as this shape, but it's either in the front cover of your book or in the appendix. I don't have it with me right now. Triangle is 1/2 base times the height. And I'm thinking this one is 2/3 the base times the height for the area. And for the centroid of a triangle, it's 1/3 from the big end or 2/3 of the base from the little end. This one, for this shape, is actually, my memory serves me right, this would be 5/3 of the base, or 5/8, I'm sorry, and 3/8 of the base. So that's something that we need to remember. Okay, so when we calculate the area, once again, area is 2/3 of base times the height. So if I said 2/3, and the base being 10 feet, and the height being 50, we get an area of 333.3. That's the area. And it's the same for both sides, as it's symmetrical. And over here, the area is going to be half the base, which is 5 times 100. That's going to give us 500 for both sides. All right, so what that means, since we're symmetrical and we load this onto our beam, we really don't even have to take moments or anything. Just by proportions, we would know that this is 333.3, and this is the moment diagram over EI again, both these. And this side is 333.3. And they're both over EI. I don't write that, it's okay. And of course here we would have reactions of 500. I'm going to leave the EI off. All right, now what we want to do, let me draw you something on slope real quick. So if we load this beam either as a uniformly distributed load or as a concentrated load, the slope at the center can be found just like with the moment area method. I'll erase this, but let's say that's slope at center line. And if we look at the areas out to the center line, so we're going to cut like a free body, center line, and I'm going to look left. All right, so I'm going to have just this. And on the other side, the other beam will have that. The area here is 500, but the reaction is 500. The area here is 333.3, but the reaction is 333.3. Remember, we do have, need to erase, we do have positive sign convention. So this is any section, x to the x, or whatever. As we look to the left of a section, up is positive, or clockwise moment. As we look to the right of a section, down is positive, or counterclockwise movement, rotation. So as we look at slope here, we got, at this point, we got 333 acting down and 333.3 acting up, 500 acting down, 500 acting up. So, as I illustrated before, the slope is 0. Okay, so I'll erase here just a second. All right, so if we look at, once again, I'm going to draw something very similar to what I just had. Here's my reaction. I'm going to need to know this distance, because this is the point that I'm interested in, the center line deflection. And we've also got the same thing here. This is 500. These areas we already know, 500 and 333.3. And I'm going to need to know that distance. All right, so remember our positive sign convention over here. So the deflection triangle center line is equal to, I'm going to start with this one, it's 333.3, and that's actually repeating, times, now what is this? We said it was 3/8 of B. So 3/8 of 10 is 3.75 feet. That's this distance here. 3/8 of V. All right. That's the positive rotation. Oh, I'm sorry. I need to renege on that. Don't need that number yet. Positive rotation is actually 10 feet away. So the reaction times 10. I'm sorry about that. And then the negative rotation, so this whole area is acting in that direction, is the 333.3 times 3.75. Now we'll go over to this part. Remember, we're adding these together. So plus, now I got my positive rotation again. That's basically my reaction, 500 times 10 minus the 500, which comes from the area, times 1/3 of 10, 3.33. And that's it. All over E, I, whatever, generally E is 29,000 for steel. And if I'm not mistaken, one of the problems in your book had E of like 1900 KSI. Well, that's more than likely wood. You remember that from a 101 class. And then whatever the I was. And then we want to multiply this by 12 cubed. So that's the moment, the method of elastic weights that can be used for simply supported. So you don't have to do the double integration method if you don't want. Moment area and elastic weights are pretty easy to get through if you can generate the M over EI diagrams cut the section wherever you're interested in solving for the slope or deflection, and then look to the left or right, either way, follow your sign convention, and generate the equation. Let me know if I can help anyone work through any of those. All right, have a good day.